So what I will do is that, wait, so I will just play the video again and just tell me if you can hear the audio of the video. Okay. As the concentration of each product raised to the power of their moles. So concentration of C. So you can hear it now? Hello everyone. Today I will be solving GATE 2020 question set of chemistry. In this video I will be solving question number 23 carrying mark 1. So this question states that at 25 degrees Celsius, the EMF of the cell, the given cell is question mark. We are given the standard EMF E naught of the cell 0.082
Ma'am, voice is not audible.
R and F well. Still not audible. I am playing it on speaker so that you
Yes.
Okay. तुम लोग को माइक्रोफोन से भी आवाज़ नहीं आ रहा है क्योंकि इसमें कुछ परमिशन इशू आ रहा है, सो मैं अभी इसको फिक्स नहीं कर पा रही हूँ. So we follow the question by first introducing you with Nernst equation. So Nernst equation. तुम लोग को माइक्रोफोन से भी आवाज़ नहीं आ रहा है क्या? ओके.
मैम आप बोल रहे हो वो तो आ रही है आवाज, बट जो सॉल्यूशन में वीडियो में जो है वो आवाज नहीं.
you can see the screen, correct? So yeah, the first question is that at 25 degrees Celsius, this EMF, we have to find the cell is given to us and we have to find the EMF of the cell. So we are given with the E naught of the cell, that is 0.082, and some constant value like R and F. So if you guys have any audio problem, then tell me, okay? I'm just So what happens is that to solve the problem, I will just go from the Nernst equation that you guys already know. I will just define the equation that we have. It has E cell is equal to E naught cell minus RT ln Q upon NF. Okay. So what are these? E cell is the cell potential at non-standard state. E naught cell is a standard cell potential. R I have as a constant is 8.314 joule per mole per Kelvin. T is the absolute temperature. So we have 25 degrees Celsius, we will convert it into the Kelvin scale, okay. N is the number of moles of electron transferred in a balanced cell reaction that we will see later. F is my Faraday constant. So Faraday constant value is already fixed, that is 96500 coulomb per mole. Q here is my reaction quotient for the given reaction. So to define Q, I will just give you one example of two reactant A and B reacting, giving me the product C and D, and the number of moles reacting is respectively A, B, C, D in small letters as shown. So my reaction quotient will become as, yeah. So this is just written as the Q is equal to activity of the product upon activity of the reactant. Okay. So I can also write Q as the concentration of my product, like C, D raised to the power of their moles upon concentration of my reactant A and B raised to the power of their mole. Also we already know, or if we don't know, then here this can be the concentration or it can be the pressure for the gas, but if it is a solid, we take it as 1. So I just want you to get familiar with the cell representation. So cell representation is basically done with metal ion. So first we write the anode. In anode there is always oxidation happening. So in oxidation, what happened, that a loss of electron take place, correct? And then there we write a salt bridge, and then the cathodic part. So cathodic part, reduction is happening, it means gain of electron will be there. So I can simply write it as anode oxidation with a salt bridge and cathode reduction. This is all for your understanding. Now to come back to our question, we have the cell as this silver, okay, solid, and then Br negative aqueous, and then the product as AgBr, which is also solid, and there is a loss of 1 electron. So this is a anodic half cell reaction where oxidation is happening. And then this is a cathodic half cell reaction where reduction will take place, that is a gain of electron will be there. So my copper 2 plus aqueous, a positive ion, my cation will take 1 electron and get reduced to copper plus, that is again in aqueous form. So overall I have to combine these two reaction of anodic and cathodic half cell to get the overall cell reaction, that will be Ag solid plus Br negative aqueous, copper 2 plus aqueous, and these two will be balanced out, so it will cancel out each other, giving me the product as AgBr solid plus copper plus aqueous. Okay, so what I have to do is I have to write the reaction quotient for my overall cell reaction. So for this particular given cell, my reaction quotient will be product, reactivity of product. So look here, on your product side we have AgBr and copper plus. Okay, so AgBr is in solid form, so we will take it as 1, and copper plus is in aqueous form, so I can write the activity of copper plus. So guys, if I am going too fast, then just type on chat box. Okay, I'll just reduce my speed. So the divided by activity of reactant. So A activity of Br negative multiplied by activity of copper 2 plus. So yeah, I have already told you that this activity, okay, this was also given in our question. So it was given as 0.24 for copper plus and 0.2 for Br negative, 0.48 for my copper 2 plus. So my reaction quotient for the given cell becomes 2.5. Now jumping back to my Nernst equation, so I already have E naught cell, I have calculated Q, I know R, I know T, N is 1 here because only one electron was involved in whole cell reaction, and we know F value also. Yeah, so at 298 Kelvin my temperature, so this is my E cell, it will just become like this. So my ln, natural logarithm, is converted into log with base 10. So here some constant value, if I just solve them, I will get the equation as minus 0.059 log base 10 Q upon N. So basically I already had my E naught cell, that is 0.082, and then I put the value of Q that I solved from the overall cell reaction, and I get E cell as 0.058 volt. So you guys have any questions? Okay, so I am attaching one NPTEL reference here. You can just look into this particular electrochemical method 1 continued lecture from Professor Debashish Ray. He is from Department of Chemistry, IIT Kharagpur. I will also attach the link for the video lecture. These all material, the pre-recorded video that I am playing in the live session, will be uploaded later in the GATE portal, so you can access it later. Okay, so for this particular question, any of you have any doubts, just pitch me in. You can type in the chat box. Okay, if not, then I will just move to other question. Yeah, thank you. So this is a interesting question. I mean, when I was preparing, I have not read about this particular topic, so I wanted to cover it this time so that I can also learn with you guys. So this is a 2-mark question. So it says that find out the correct plot for the E versus time. Okay, so voltage versus time, and this is called as the excitation signal, which is used in a cyclic voltmeter. Okay, so there are 4 options given. So basically, if we don't know anything about cyclic voltammetry, we will not be able to solve it correctly, and we will not be able to judge which one is correct for the E versus time, but if you have just learned a simple basic of cyclic voltammetry, it will be very easy for you. So in this video I tried to make some basic concept clear. So let's just see. Okay, so yeah, so cyclic voltammetry, CV as we denote it, is an electrochemical technique, okay, which measure the current. So you guys are not getting echo. Okay, cool. So yeah, so it is an electrochemical technique which measure the current, okay, that develops in a electrochemical cell under condition where voltage is in excess of that predicted by the Nernst equation. Actually this particular definition was not very clear to me, so I will just try to make it more clear to you by some representation to what is happening there, so that you can just get the basic of cyclic voltammetry. So first we have a potential state, okay. So potential state is just an analytical instrument. It is designed to control the working electrodes potential in a multi-electrode system. Like in cyclic voltammetry we already have 3 electrodes, so it is a multi-electrode system, and in 3 electrode there is one working electrode, one counter electrode, and one is a reference electrode, okay. So potential state is designed to control the working electrodes potential, and yes, and after that what happen is so potential state apply a triangular type of potential waveform to the electrochemical system that we have to measure the resulting current. So this potential versus time, which was actually asked in a question, is the one potential that is applied from the potential state to our electrochemical system, okay. So what happen is this is some kind of a triangular potential waveform. This is a very basic, it can be different form also, but it is the classic one, okay. So potential state apply this potential to our electrochemical system and then measure the resulting current. So the current is measured is versus time at first, but this is not what we see in a cyclic voltammetry. What we see in a cyclic voltammetry is that the okay, so we see this current versus this potential. So you can just so in this technique this potential state apply a triangular potential waveform to our electrochemical system, as I have said already, and then we measure the resulting current. Yeah, and the triangular potential waveform is made up of potential sweeps. You can just have a look of this triangular form, and potential sweep meaning it changes its form, like from increasing it changes from positive to the negative potential. And this sweeping is happening as a linear functional form, okay. So you can see we are sweeping the potential linearly as a function of the time, and the measured current is also measured as a function of time first, but finally we plot this measured current as a function of applied voltage, and thus we get a cyclic voltammogram. So you guys have any doubt in this? Okay, so I will move to the triangular potential wave function, because my whole question is based on this particular section of the cyclic voltammetry. So the potentiostat which is applying this kind of potential to measure the resulting current. So one is the classic triangular potential wave function which is applied. So this is a potential versus time plot. So there are several parameters to this plot. We have initial potential, okay, yeah. So there are basically 4 parameters. So one is the initial potential, which is the start of the experiment. So this is my initial potential, from where my experiment start. The switching potential, it defines the end of the first segment. So this is the linear form that you can see. It is the first segment and it ends here. So this is called the switching potential. So this potential value corresponding to this particular value is called the switching potential. And after this we get another segment which is called as segment 2, and so that I can reach to the final potential value, it defines the second segment of our linear sweep completing the triangular wave function. So basically it completes one cycle in a cyclic voltmeter. And the fourth parameter is the sweep rate or the scan rate. It is just the slope of the linear sweep. So if I find the slope of this, so this will be the sweep rate or the scan rate. So a cyclic voltmeter experiment may consist of one or multiple cycle. So here we have only seen one cycle. Okay. So there are some tips. So yeah. So parameter of the triangular potential and number of segment. Okay, so here I have shown segment 1, segment 2, and these are the 4 parameter. We can just adjust these depending upon our electrochemical system what we have. The classical triangular potential waveform is not strictly followed, but it is the basic one. So you should know that this is the basic one in a cyclic voltammetric experiment. So in CV experiment, you must consist this potential form must consist at least 2 segment minimum. Okay, so these are the tips you should keep in mind, and let's just move ahead. So these are the 3 different excitation signals from our potentiostat that we can have. You can see that here you have all the parameters in count, so you are not violating anything which is not in cyclic voltmeter. So yes, so these can be the potential, this can be the, we can have these in our multiple choice also if you are facing the same problem in some in your gate paper. So these can be the equally probable answer for the question that we have. So coming back to my question, so what was asked is the E versus time, that was the excitation signal, okay, in cyclic voltmeter. So you can see that I have one very probable answer, that is C, correct. This is the triangular waveform. It is not violating any 4 parameter that we have discussed. It has minimum 2 segment, it has 1 and 2 cycles, and yes, but also okay, so this is my correct answer for this particular question. But also just to get you a little more familiar, that this particular E versus time plot is for the linear sweep voltmeter. Okay, so here it is just increasing linearly and there is no switching potential here, so this belongs to the linear sweep voltmeter. Okay, so when I was making this video, I will be very honest with you that yeah, this is one book for the electrochemistry. You can go with this book reference, Electrochemical Method Fundamental and Application by Alan Bard. Okay, and the NPTEL reference for this is the lecture number 25. So there Professor Tamal Banerjee have discussed a lot of details for the voltammetry and galvanostatic charge and discharge, but you can also, I am also attaching one YouTube source, so this is also very helpful for someone who doesn't want to go in whole detail but want to know the basic brief knowledge. You can go with this YouTube source also. It is a authenticate source also. So yeah, anyone, any doubt? So you got the concept. So B and D, so so B and D, there is potential sweep is happening, but it is basically monotonically increasing only. It is not going in the negative potential. So in cyclic voltmeter, if you just go, I have only discussed till the excitation signal, but I have not discussed in my video what happened after we get the current versus time plot for my electrochemical signal. We just plot it for my current versus the potential that I have applied. So it is done because I need the oxidation and reduction both. So in my electrochemical system, to make the oxidation and reduction, what we do the switch of potential. Okay, first we increase the potential, for example we increase it, so maybe there is some oxidation happening, okay, let's just say it, and then when my potential is swept, meaning my is switched, it decreases, it goes to the negative direction. Let's say first oxidation was happening, now the reduction will happen. So for that to happen in a cyclic voltmeter, so there should be one cycle which should be completed. So actually I don't know what B and D belongs to, but it is definitely not a cyclic voltmeter because it doesn't go with the parameter that we know. Okay, it is not going for the switching potential, it is also not going in a negative direction after a time. So it should be in a cycle. Okay, first if it is increasing, then it should be decreasing also. Okay, anyone else? So this is the third video. Yeah, so for this particular video I have searched a lot of theories so that I can actually get why this is a beta decay, why this is not an alpha decay. So I will just try, I mean most of you guys have already know, but yeah, okay. So this question state, this also came in 2020 gate paper chemistry. This question carry 2 marks, and it states that the fission reaction of this uranium 235, so it is a fission reaction, okay, so 235 with thermal neutron, this will give me 2 fragment, okay, and this will again go for radioactive decay like x1, x2, x3 product will be there, y1, y2, y3, y4 product will be there, and they have stated that this x3 and x4 are stable nuclei, and what are these? We have to find x3 and x4. So yeah, so what is a radioactivity? It is just it is a cause of when an atom, for whatever reason inside the nucleus, some nuclear forces or something, it just want to give away some of its energy, and the nuclei of these element are unstable and they decompose or decay spontaneously with the emission of alpha or beta particle. This leads to the formation of some new element with different physical or chemical properties. So there are types of decay. You might be familiar with these kind of decay. So alpha, beta and gamma. Okay, so alpha, alpha is basically the helium nucleus. It carries the charge 2, mass 4. It has a very minimal penetrating power because of its high mass. And beta particle are basically electrons carrying charge -1, mass 0. They have a penetrating power a little higher than alpha particle, but it is also short. Okay, and gamma rays are basically some electromagnetic radiation with 0 charge, 0 mass, and they have a very high penetrating power. So these are the type of decay when my element go to the radioactive decay. So the theory of radioactivity. So the theory of radioactivity is that the nucleus whose N/P ratio lies outside the belt are unstable. And what belt I am talking about? When I am plotting the number of neutrons versus number of protons, there is one belt which is known as the belt containing stable nuclei, and all the elements falling under this N/P ratio value, they are known as stable nuclei. Okay, and this dotted line is just represented as N/P equal to 1. So the nuclei with N/P ratio lying above or below the belt are unstable. So above or below are unstable. So they undergo radioactive disintegration. They will give up some alpha or beta particle in such a manner that they will come back to this stable region. So case 1 is just consider a nuclei with N/P ratio lying above the region of stability. So for above the region of stability, this means that the nucleus will contain too many neutrons. So N value is higher than P. In order to attain the stability, it will emit a beta particle. So it will emit some electron. In this way, neutron changes into proton and the N/P ratio get lowered and comes closer to the region of stability. So one example for this is the disintegration of isotope of carbon. So 14C, it will emit one beta particle, and so emitting one beta particle is there to maintain the electrical neutrality. Here -1 is here, so my charge will increase as 7 here, or atomic mass remains same, so it becomes nitrogen. So N/P ratio from 8.8/6 it goes to 7/7. So that is from 1.33 to 1, that is coming closer to this region. This is just an example. Vice versa is that the case number 2, where my N/P ratio lying below the stability belt, it will go it basically contain the excess of proton. So it will disintegrate in such a way that the new nucleus has a higher value of N/P and therefore lies closer to the belt. So this happened by the emission of an alpha particle, that is helium nucleus will be emitted. As a result, the new nucleus has a lower charge and lower mass. So basically the unstable nuclei continue to emit alpha or beta particle until a stable arrangement is reached. So I am giving you one tip, but it is not strictly followed. Even it is not strictly followed in this example, but you can just go with this tip, that N/P ratio equal to 1 is only for up to element number 20. Like N/P ratio between 1 to 1.6 is known to be stable nuclei, and for the ratio above 1.6 and below 1 will be unstable. So for our example, so this particular element is having the ratio, so n value, number of neutron value is 58, okay, upon 41. So you can just separate 99 up and 41 so that you can get number of neutron, and then you do the ratio, you will get to know that it will do the beta decay, okay, because we have n value higher than proton. Same with the other and element. So we are getting for both of them beta decay. So you can just go checking all your n upon p ratio, and you will find out that we are getting beta decay in each step. And for the second one, you can just go with the same procedure, and you will find out that we observe the beta decay in each step, again getting the stable nuclei cesium here. For this I have followed addition to 2001 principle of physical chemistry Puri Sharma Pathania, and also you can check out this NPTEL reference for the radioactivity alpha decay by Professor H.C. Verma. You can just check out this theory of radioactivity, that particular plot that I have discussed. So yeah, this NPTEL reference is also there. I have also attached one YouTube link to that. Yes. So ultimately our correct answer is the option number B. Okay. Yeah. So sorry guys, this video glitch, I will fix it for the next time. So any question from this particular question? Okay, so actually I need some feedback from your side. I mean, wait. So first of all, I want to know that do you guys want us to solve those aptitude question also, other than the chemistry part? Okay. You can give your vote in your chat box too. So you guys have attended live videos of other fellow mates for chemistry? Ashish, you are saying yes for the second question or the first one, the aptitude one? Okay, so you have attended those live sessions. Yeah, great. So any feedback from your side? You are okay with this playing video and then asking questions? Okay. So all of you are doing your masters, integrated PhD? Okay. Okay, okay. So you guys are preparing for PhD entrance and all. Okay. So where are you guys from? Okay. Okay, nice. Yeah, so I haven't introduced myself yet. So I'm currently doing PhD from IT Kanpur. So my field, research field is theoretical and computational chemistry. Okay, so yeah, so that's why I will be majorly doing physical chemistry questions. So that's it. You guys have any general questions or anything? We have 1 minute left. Yeah, yeah, sure. So basically, in any theoretical and computational chemistry, if you go there is one we develop method. Okay, so developing method basically is the one that we use in Gaussian, ab initio method, CPMD. So one part is working on the developing of the methods, or the other part is working with those method and using it to in our some simulation and all. So I am working in the simulation part, so I use those method already developed, like Gaussian software, Gromac software, and LAMS is also there. So currently I am doing spectroscopy theoretically. Okay, anything else? So you completed your master from Punjab, Ropar, where? Okay, okay. Okay, okay, good, good. Okay. Okay, yeah, thank you so much.